In this presentation, we delve into Python's multi-threading and multiprocessing capabilities. We'll explore how these concurrent execution patterns enhance application performance and resource utilization in modern computing environments. Concurrency in Python is crucial for modern applications to handle multiple tasks efficiently. The Global Interpreter Lock, GIL, limits true parallelism in multi-threading, necessitating strategic solutions. Multiprocessing bypasses the global interpreter lock by using separate processes, ideal for CPU-bound tasks, while multithreading is best for I/O-bound operations like network requests. The global interpreter lock, GIL, is a mutex that allows only one thread to execute Python bytecode at a time. This limits multithreading's effectiveness for CPU-bound tasks, as threads can't run Python code concurrently on multiple cores. Despite multiple threads, only one executes at a time, hindering performance in CPU-intensive operations. Python's threading module offers high-level interfaces for concurrent thread management, ideal for input/output-bound tasks like network requests. Threads share memory space, enabling efficient data exchange but necessitating synchronization to avoid conflicts. Example: a thread executing a worker function, demonstrating thread creation and management using threading. Thread. Threads offer lightweight, concurrent execution ideal for I/O-bound tasks, sharing the same process memory. This allows for efficient data exchange and responsive application behavior, as threads can perform parallel waiting operations, enhancing performance without the overhead of multiple processes. Python's global interpreter lock, GIL, restricts true parallelism in multithreading, limiting CPU-bound tasks. Race conditions arise when threads access shared resources without coordination, leading to unpredictable outcomes. To manage thread safety, Python offers synchronization mechanisms like lock, rlock, semaphore, and event, ensuring coordinated access to shared resources. Multiprocessing in Python enables true parallel execution by creating independent processes, each with its own memory and interpreter. This approach bypasses the global interpreter lock, effectively utilizing multiple central processing unit cores and preventing race conditions. The multiprocessing module's application programming interface mirrors the threading module, easing the transition for developers to process-based concurrency. The multiprocessing module offers essential components like process, pool, queue, pipe, and lock for managing concurrent processes. It supports cross-platform functionality, running on Linux, macOS, and Windows. This module enables both local and distributed computing with advanced inter-process communication through queues and pipes, allowing for complex parallel computing workflows. To create a process using multiprocessing, process. Instantiate a process object with the target function and arguments. Start execution with .start, and synchronize completion using .join. This ensures the main program waits for the process to finish. Remember, the if name equals ..main ..guard is crucial on Windows to avoid recursive process creation.